So we have already seen row echelon form, right? The Gaussian animation idea is about the row echelon form only. But there is one more form that is just after the row echelon form, which is called row reduced echelon form. If you want, you can just study this particular topic, or otherwise you can leave this video. This is completely optional video. Okay, just to give you one information, I wanted to make this video. So let's just see this row reduced echelon form. See, row echelon form you already know, right? Row echelon form we already know. But now I'm telling you row reduced echelon form. Okay, that's the only difference. Let's just see this. This is called reduced echelon form or row reduced echelon form. See, similarly, the earlier we used to call it row echelon form. Row echelon form, it is just name, like nobody is going to ask you the name, but still, earlier we used to call it row echelon form or echelon form only. Echelon form only. Similarly here also, either we say row reduced echelon form or reduced echelon form only. Reduced echelon form. So it is just a name, nobody is going to ask you. Okay, so let's just see this reduced echelon form or row reduced echelon form. See, earlier we used to have this kind of matrix and we used to say that this is called echelon form or row echelon form. But now our objective is to convert this into something like this. So what is special about this? What is special among these two? What is difference between these two? Is that, like, first, given a matrix, you will convert that to a row echelon form, and then you take some extra elementary row operations. You do some extra elementary row operation, and then you convert that to a row reduced echelon form. So what I mean to say is that you have, okay, let me just tell you that what I mean to say. Let me go to the next page. So suppose you have some matrix. Let's suppose your matrix looks like this. The exact values I'm not interested, but yeah, let's suppose your matrix look like this. And then what you do to your matrix, let's suppose this is A, you convert that matrix to row echelon form. Row echelon form, right? And then you do one more or maybe few more row elementary row operations, and then you convert that to row reduced echelon form. Reduced echelon form. So that's just an extra step we are doing. And then now can you see that what is difference between these two? One thing is that you can say that, okay, I made this as one, I made this as one, I made this as one, probably, right? These three are one basically. So the pivot elements are one in row reduced echelon form. In row echelon form you can have anything, but in row reduced echelon form we have pivot elements are strictly as one. Okay, so pivot elements are one in row reduced echelon form. So this is one thing that you have noticed, that okay, these are the pivot elements, these are one. So how to make them one? Suppose that this is 5 and then this is 3 or whatever, right? You can divide this particular row by 5 and then you can make it one, because that's what you can do in elementary row operation. We have seen that we can replace this ri by some constant c1 into multiplication of ri, right? So here, if this is 5, then you can make this constant as 1 by 5, which means you can divide by 5 also. So that's the one kind of elementary row operation, and after that you can convert a pivot to 1. That's very easy. But apart from that, do you see something else also? See, if you notice, then here all the elements are 0 below this, all the elements are 0 below this, because that's what we call pivot in row echelon form, right? But here all the elements are 0. That is okay. That is fine. But if you notice here, all the elements below this is 0, but above this is also 0. If this is pivot, all the elements below this is also 0, above this is also 0, right? So I can say that, this is the definition, and not I can say, basically this row reduced echelon form. Let me go to the next page. Row reduced echelon form. Now here I can say it is basically same as all pivots are 1. All pivots are 1. This is first point. And then all elements below and above, elements below plus above pivots are 0. So that's the difference. See, earlier I only had below, but now above also. Okay, so that's the difference. let's just see that how to make them 0. Let's not worry about that how we are going to convert from here to here, like we will see. But for now I'm just telling you the definition. Okay, this is the definition of the row reduced echelon form. So as you can see that the definition is also written here. Cool, which I have taken from some standard university. Okay, now let's just see that how to convert given this matrix to a row reduced echelon form. Now suppose we did something, some using some elementary operation. Actually this is one of the example that we have already taken in one of the lecture, but anyway, like let's not worry about it. So basically we converted to this, and then we finally got the matrix which is actually looking like row echelon form, right? These are the two pivot and all of them are 0. Okay, now can you convert? Now my task actually begins from here. That's why I'm not interested to go from here to here, because for this lecture I'm just assuming that you can convert from here to here using the elementary row operations. Now can you convert further to it that into row reduced echelon form? Yes, let's just do it. Okay, first let's just make all the pivot elements as 1. So let's just make all the pivot elements as 1. So this is already 1. Fortunately I don't need to do anything. This is already 1. And then to make it 1, because this is also pivot element, I can divide by -2, right? That's one easy elementary row operation I can do. R2 can be divided by 1, R2 can be multiplied by -1 by 2, R2, something like that, right? So basically this is 0, this will be 1 in that case, this will be also 1, this will be 4, and then all are zeros, right? Okay, now these are the pivot elements. Now tell me, is this the row reduced echelon form now? Have you reduced it? No, right? To reduce it completely, what you need to do? You need to basically check whether all the elements below and above also 0. So below, that is okay. Here below is 0, but above is not 0. So let's just make the above 0 also, which means I want to make this also 0. So how can I make it? You can replace this R3. You can, R1 by R1 minus 3 R2, isn't it? If you replace this R1, this particular element by R3 minus 3, then it will be 0. And fortunately, it won't impact this. That's the beauty, because you are having 0 here. That's why it won't impact this. Okay. So let's just do it. So it will be R1 minus, okay, if you do subtract here, doesn't matter. And then 3 minus 3 will be 0. And then 1 minus 3 will be -2. And then this is 9 minus 12, which will again be -3. Okay, this will be -3. And then you are not replacing anything else. So this will be 0, 1, 1, 4. And then all are zeros. And then finally, you got row reduced echelon form. Amazing, isn't it? Obviously, you must be having a doubt then that what the hell is going on, or maybe, pardon my language, I mean to say that why we actually want to do this, right? You may be wondering that why we are actually converting that to a reduced form. I just give you a minute. Just think about it. That what's very good thing about this particular matrix that is not here. Okay, that was not in the echelon form, but that is in a reduced echelon form. So what is something special about this? Just think about it. See, these are the vectors that you have here in the pivot element, which is basically very convenient vectors, isn't it? Suddenly you got very convenient vectors. Now the good thing about it is this, that you say that these are the pivot. Earlier also you were saying these are the pivot, right? Earlier also you were saying. Now also you are saying the same thing. But now you can say that these are the pivot, these are the dependent columns, which are the free columns. This is the free column, this is also the free column. But the good thing about it is this particular matrix is that since you have the most convenient columns, that is why you can immediately find the coefficients. Let me just tell you that what do I mean by all of this story. See, you started with this, right? Okay, maybe I can do one thing. Let me just minimize this. Okay, see, you started with this matrix, you got this matrix, you did something, you got this matrix, you did something, you got this matrix, you did something, and then you got this matrix. Ultimately, you found out the reduced form. Now, if I just ask you, can you represent this particular vector as a linear combination of these two vectors? Because it is a free, see, first it is a free column, then it must be represented, right? Earlier I told you that, okay, see, this is the pivot, this is a pivot. Earlier also I told you that it is a free column and you must be able to represent it, but I was not able to convince you that what are the coefficients. I mean, I can give you the long method maybe earlier also. I can say that, okay, that, see, trust my words, that you can represent it using these two columns, and then you can find the coefficient using the set of ax equal to b. I mean, if you really want me to solve it, I mean, earlier I can say that, see, this 1 0 0 3 minus 2 0, that can, the linear combination of these two can represent this 1 minus 2 0. And what are the coefficients? Let's not I mean, I don't know about the coefficients, so I can solve for the coefficients, right? This is x, I can solve for the coefficients. So earlier I was not having very convenient vectors, so I told you that, okay, if you want you can actually solve for the coefficients, but now I have the convenient vectors. So that's the beauty about reduced form. Now if I just ask you that, can you represent this particular vector, whatever vector you have got, this particular vector, as a linear combination of these two vectors, then you will say yes, why not? I mean, immediately you will say that you can represent like this, minus 1 minus 2 1 0, and that can be represented as a minus 2 into multiplication of 1 0 0 plus 1 0 1 0, isn't it? So that's how you can represent this column. Similarly, if I just ask you that, can you represent this column, then also you will say why not, which means you can represent minus 3 4 0 as a linear combination of these two, minus 3 1 0 1 0 0, and then plus 4 0 1 0, isn't it? Very easily you can represent. Great. Now I know that some joy I can actually understand some joy on your face, but that won't just stop here. The good thing is that like, there are more interesting stories to tell about it. And the interesting story is that this particular vector can be represented as a linear combination of these two vectors. But if you remember from our previous discussion, okay, I told you that if this vector is a linear combination, okay, which is, let's say, minus 2 into this and 1 into this, just the previous video if you remember, then this also minus 2 into first, and then plus 1 into this, right? This also, which means what I mean to say is that, see, let me just remove all of this. Okay, let me just remove all of this. What I mean to say, that if I just tell you that this vector is minus 2 into first vector and plus 1 into second vector, similarly this vector also, because the linear dependency between the columns hold, which means 1 1 0 can also be represented minus 2 as 1 0 0 plus 1 as 3 1 0. Let's just check. Minus 2 plus 3 is 1. Yes, minus 2 plus 1. This is okay. This is 0 plus 1. Yeah, 1. And then 0 plus 0 is 0, right? So you can represent this vector also. Similarly, not just this vector, you got the coefficient for this vector. You have the coefficient for this vector, 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 you have the coefficient for this vector. Which means the linear dependency holds. And that's the beauty about this particular Gauss elimination. See, now if I just ask you, like earlier I told you that this is the free column, right? Now if I just ask you that, can you tell me the coefficients also, then you will say, okay, give me the row reduced form. I gave you the row reduced form. This is the row reduced form. You got the coefficient, which is minus 2 and 1. Great, awesome. Let's just represent it. Minus 2 into first column. What is the first column? 1 1 3 1 1 3 and plus 1 3 1 11. Just check. Minus 2 plus 3 will give you 1, right? Similarly, minus 2 plus 1 will give you minus 1. Minus 6 plus 11 will give you 5. Isn't it? And not just this, you can represent this also. See, if I, okay, due to the lack of space, I'm going to the next page. See, I have told you can represent this. You can represent any of this vector, 1 minus 2 2, as a linear combination of the coefficients. You can you know that minus 2, the linear dependency, you know, minus 2 into the first vector, which is 1 0 0, plus 1 into the second vector, which is 3 minus 2 2, right? Let's just check it. Minus 2 plus 3 1, 0 minus 2 0 plus 2 plus 2, isn't it? And not just this vector, there is nothing special about this vector also, because this is also free vector, right? So you can represent 9135 by a linear combination of these two vectors, and which is minus 3 and 4, right? Minus 3 of the first vector 1 1 3 plus 4 of the second vector, which is 3 1 11. You can just check it. This is 12 minus 3 9, minus 3 plus 4 plus 1 minus 9 plus 44 is 35, right? So you can represent any of this vector. So basically, like last time I told you that okay, these are the free columns, and I mean linearly dependent columns. So can you can represent as a linear combination of the pivot columns. But this time I'm also telling you the coefficients, that what are the possible coefficients. This is the beauty about row reduced echelon form. I hope you understood this completely. You can check it throughout. You can represent this vector also as a linear combination of these two vectors. And what are the coefficients? Minus 3 and 4 again, right? Because the linear dependency holds throughout between the columns. Okay, cool. Now let's just solve this question. Let A be the 3 by 4 matrix whose column space. Okay, sorry, let's not worry about these things. Okay, A. Basically it means let me just write in other words, that has basically three pivot, okay, which has 3 pivot columns. Actually the earlier wording was, maybe if you are little interested, then I can just tell you that what was the earlier wording. Otherwise actually it's not needed, as you also know, but yeah, just for your sake of interest. See, earlier wording was something like this, that column space dimension, they were talking about the column space dimension, right? So column space is basically the space or the vector space that you form using the columns of the columns of our matrix. And the dimension of vector space is something very unique and something very special thing. See, if I just ask you what is the dimension of this vector, then you will say that it is 3, right? Because these are the 3 numbers. Then dimension of this vector is 3, which means it is in R3. But dimension of vector space is not like this. Dimension of vector space is basically, like technically I'm speaking, that it is the number of vectors in the basis set, which means the minimum number of vectors that can span that particular space, that is called dimension of the space. Okay, so if I just say that okay, these are the 2 vectors, okay, whatever the vector dimension, see, vector dimension and vector space dimension both are different. See, let's suppose this is the vector dimension, which is a 4, this is another vector dimension, which is a 4, and all of the linear combination of this will make some space, right, some vector space. So that vector space has just dimension 2. Although the vector dimension is 4 4, but the vector space dimension that they will span, okay, is 2, because there are just 2 vectors that can span that vector space. So vector space dimension is little different, and the vector dimension is little different. Anyway, it's not important, so obviously like I'm not going to talk about it further, because it's completely irrelevant for GATE, but just for your sake of curiosity, I just told you. Okay, okay, so a matrix which has I can say, which has a 3 pivot columns. Okay, this is the wording of this particular question. Just consider this as a wording. Now what they are saying, consider the following matrices. Okay, these are the matrices. Which of the above could possibly be the reduced echelon form of A? If that is a free pivot, 3 pivots, first of all let's just see how many pivot. 1 pivot, second pivot, third pivot. Okay, 1 second, okay, and then I think this is the third one, right? Cool. 1 second. Okay, the third is not even the option, because it is a 3 pivot. Okay, either first or second, right? Now let's just check. In the first, is this reduced? Yes, this is reduced, right? Because all the pivot is having below and above 0. Is this reduced? No, it is not. Not even the echelon form, right? Reduce is so far, but it is not even the echelon form. So that's why A is the correct answer. 1 only, right? Okay. Let's just check that how many of them are in the row reduced echelon form. See, is this the row reduced echelon form? This is the pivot and this is the pivot. So above, below, both are 0. Yes, I think this is in the row reduced. Is this is the pivot, this is the pivot. Okay, above is not 0, so that's not. What about this? This is a pivot, this is a pivot. Okay, above, below. Okay, above, below. I think this is also right. So that's how easily you can do these questions, whether it is row reduce or not. So you can do this particular question as an homework. I have the solution on the next page. Okay, so this is the solution of the homework question that I just showed you. So you can do this question, which is saying which of the following matrices are in the row echelon form, which of the following are in the row reduced echelon form. Okay, so you can do this easy question as an homework. The solution is on the next page. Now let's just do this question. They are saying bring all the matrices to the reduced echelon form. So let's just do this. Let's just do for a couple of matrices, maybe A, B, and then you can do for I think C, D, right? So let me just do it for A, B. For A, I'm saying this is 0. So let me just interchange it maybe. Okay. This is 1, 1, 1. This is 0, 0, 1. This is 0, 2, 0. Maybe I could have wrote the 0, 2, 0 above and 0, 0, 1 below. Okay. Just interchanging few rows so that like I can do my work easily. And then this is 0, 0, 1. Okay. So see, now it is already in the echelon form. You need to convert that into the row reduced echelon form. Because that's what they are saying. Reduced echelon form, right? Okay. So I think I can replace this R1 by R1 minus R1 can be replaced by R1 minus maybe you can replace by 1 by 2 R2, something like that, right? R1 can be replaced by, see, if you do R2 minus, then it will be a problem because it will be minus 1. Then, I mean, you can do it, but ultimately you have to divide by minus 1. So let's do R1 minus only. R1 minus, I think it will be 1 by 2 R1, 1 by 2 R2, right? And then this will be 0. Okay. So let's see after that what you are getting after 1 by 2 R2. So it will be R1, you are subtracting this minus 1 by 2 R2. So you are subtracting 0, 1, 0 basically, right? 0, 1, 0. So it will be 1, 0, 1, 0, 2, 0, 0, 0, 1, right? Okay. So, okay, first of all, I mean, before doing all of this, let me make this as 1, right? So let's just divide by 2 and let's just make this as 1. I think, yeah, and then it will be easy to do. Okay, so I think I can do R1 can be replaced by R1 minus R2. Yeah. So R1 minus R2 means this will be 1, 0, 1 and then 0, 1, 0, 0, 0, 1. Yeah, I think we got the same result, but anyway, like that's the best practice because anyway I have to make the pivot as 1. So now ultimately you need to make this also 0. So how you can do it? You can replace R1 by again R1 minus R3, I think, right? And then you can make this also 0. So it will be, I think, 1, 0, 0, 1, 0, 0, 0, 1, 0. I think I just got the identity matrix, right? Okay. Now this is a row reduced echelon form. These are the most convenient vector, and since every vector is having the pivot, like every column is having a pivot, so this way there is no free columns, right? Okay, great. You can do the rest of this BCD. I'm not doing it because this is just elementary row operation. I hope you can do it. Okay, just try it out. It will be a good exercise. Just try it out. Now let's just do this particular question, which is very nice question to be honest. Okay, this is ultimately nice question. I mean, I really like this question. When I was putting this question in the slide, I was just thrilled that, okay, this question is very, very nice. So what they're saying that consider matrix A and they have given the reduced form also. Okay. So now they are asking for the values of A plus B plus C, C plus D. So how you can do this question? How you can approach this question? Just think about it. See what they have given you. They have given you a matrix, right? And then they are saying that you don't know, but using some unknown elementary row operations, you got something. You got some matrix which is looking like this. And that's what you got using some unknown elementary row operations. Okay. Now just pause this video and just see if you can solve this particular question. Then they are asking the value of A, B, C, D, or maybe like A plus B plus C plus D. See, one thing you know, now let me just solve this, that after this, unknown elementary row operation, one thing you know, this vector can be represented as a linear combination of these two vectors, which means this vector which is AC can be written as A into 1 0 plus C into 0 1, and that should follow throughout, which means this vector also can be represented like this, equal to A into 1 0 plus C into 3 2, isn't it? Now from here, if you try to solve for A and C, then you can easily solve. How? I think using this equation, you can say that 2C equal to 4, right? I mean, you can solve it, but let me quickly do it, which means C equal to 2. And then you can say that, okay, if C is 2, then 6 plus A is 1, then A means minus 5, right? So A and C you got. Similarly, you can do for B and D, which means you can say, let me try doing it for B and D also. So A and C are done, which are 1 and minus 5, I think, okay, which are 2 and minus 5. And now let's just represent this vector, which is 0 minus 2, 0 minus 2 as a linear combination of these two vectors, which are basically B into 1 0 and D into 3 2, right? So from here, 2D equal to minus 2, which means D minus 1, which is B minus 3 is 0, which means B is 3. So 3 minus 1 and then 2 and minus 5, and they're asking for the summation, so I think you can just sum it up. This will be minus 3 plus 3 0 and then minus 1, right? So D is the correct answer here. So that's how easily you can solve this question, but it was a nice question. I mean, if you want, what you can do, if you don't know all of this story, which means that the linear dependency between the columns get preserved. If you don't know all of this story, then you can actually try to convert that into the elementary row operation, and then into the reduced form using the elementary row operation. Then you can just find out the value of ABCD. That's also one possible way to do it. Okay. So this actually, there is a little funny meme that I made. There is no this meme is actually not the reality. So it is a funny meme. Like this row reduced form actually given by the Gauss and Jordan, two scientists. So Gauss I already told you in the fundamental videos, but there is one more scientist which is Jordan. So Gauss and Jordan both actually given this row reduced form, and only, as you know, the Gaussian animation is the most popular one, which means the only the row echelon form that is given by the Gauss. And coming to the row reduced form, it is given by the Jordan and Gauss both. So it is just like a meme that Gauss is saying that, okay, since Gauss has actually designed the row echelon form using the Gaussian animation, so Gauss is saying that, okay, I'm done. Like after the Gauss elimination, after the echelon form, Gauss is saying that, okay, I quit. Like I don't want to do after the echelon form. Then Jordan is saying that, okay, you can do it. Gauss is saying, no, I can't do it. Jordan is saying that, okay, let me just help you. And then that's where the row reduced echelon form has been invented. So Gauss and Jordan both actually invented it. So Gauss has invented only echelon form, and then Jordan has helped him to invent this row reduced echelon form. So just a funny meme that I wanted to make. It is no coincidence with the reality. Okay. And now it is a time for shameless self promotion, which means that let's just promote Go classes at the same time. So if students are saying that before the Go classes I quit, and then Go classes will say, okay, you can do it. Students are saying, no, I can't do it. And then Go classes will say, okay, let me help you. And that's how you got the admission into IITs or ISC or PSU or whatever you prefer, right? Okay. So this is just like I wanted to share just a meme with you. I hope you liked it. So thank you so much, everyone. Let's meet in the next video. Okay. Thank you.